Well, one of my cats, Dandelion, is around here, although it's very dark, so I can't see him. Oh, I just felt him. That's a fluffy tail. I don't know if you'll be able to see him. Let's see if we can get a little Dandelion cameo, though. Cat meow. Cameo. Hey, Dandysaur. Oh, yeah, you guys are not going to see Dandysaur that he... Come here. Dandelion. There's my Dandelion. That's my Dandelion. So, that's a nice start to the stream. Anyway, I'll be petting Dandelion in the intro. Let me note that today, well, I'll pull open our computer graphics portion of this. We will be looking at some graphs, as we do in some of our streams, and sometimes I like to have a particular theme to the graphs we do. Today's theme is playing around especially with factorials. And factorials, as many of you know, are typically multiplying all the whole numbers up to some point, and typically don't really have a definition, or, they don't make sense to ask what is the factorial of a half or a negative number. However, they can be extended. They can be extended particularly with something called the gamma function. And just to pull open gamma function, just to show you folks how we'll see what Wikipedia says about it, it extends the factorials. It is unfortunately offset by one, and so Desmos here, where we're going to do our graphing, is going to be taking the gamma function for the in-between values and negative values, but it's going to offset it by one so it matches what the normal factorials do. Now, the gamma function is essentially, you can sometimes design functions almost to have some sort of purpose or fit some conditions, and this wanted the conditions of matching the factorials at all of the integers, but also having other conditions that would make it a nice, well-behaved function. Turns out they were able to find/invent, depending how you feel about the discovery versus invention of math, a function that works for that, the gamma function. So that's going to be what Desmos is going to be extending it with. And, let me just note, since I like to note in the intro, that what's going on recently in the combo realm, I do have a pretty new episode out, just a couple days old, about a natural phenomena where mathematics showed up, prime numbers and semi-primes showing up in nature. So make sure after the stream, if you haven't seen that yet, click the link in the description to see how prime numbers show up in nature in a cool way, and how something happened this year that won't happen again for exactly 221 years. Although, as one of the comments unfortunately pointed out, humans better be nice to the environment if we want this to even have the chance of happening again in 221 years, because the ecosystems are being somewhat destroyed by humans. So let us, respect plants and animals, and that does mean things like acknowledging the human role in cutting down rainforests, global warming, and such. Now, in general, hello to everybody who is talking here. Now, Mike Bolt here says he's proven something about my prime flip problem. That's really cool, Mike. That's extra cool because my next episode is actually going to relate. And, let's put a background visual while I chat about this. Let's show what Desmos had on their front page today. It's all these graphs have these definitions and curves, and I'll just fiddle around with them while I do this intro chatting. Mike Bolt, that's quite cool because my next episode was almost going to be about stuff similar to prime flipping. It's about a concept I now call prime glitching that includes prime flipping. It is a way of reinterpreting prime factorizations in an iterated way. And it includes prime glitch or prime flipping that I mentioned earlier, but it also includes another one that got me incredibly carried away. Now, this is a time where I discovered something that I couldn't find elsewhere, and I did eventually find it on the OEIS, the Online Encyclopedia of Integer Sequences. However, there was a very limited amount of data for this simple question, and many of the facts, all I could find, were citing that we knew things about numbers up to a certain point, but they hadn't been proven yet. Now, I have proven some of those things. I think this next episode, which is sort of the mathematical finale of the main grade -2 before we go to grade -3, there will be 2 more episodes on my main combo class channel, but one of them, the last one, is sort of a documentary-ish finale. So the next episode is the sort of mathematical finale of the grade. And the reason I'm treating it as such is, even though I discovered this phenomena very recently, and I've only been playing around with it for a few weeks, many other concepts I wanted to talk about or have talked about are tying in to it, and I genuinely believe I have proven something for the first time about a very simple problem. So it's related to prime flipping. So now, I've been very bad about responding to combo emails and stuff, but Mike Bolt, send me an email, combouniversity@gmail.com, and I will check it for your prime flip results in case I want to include them in the next episode. And of course, if I include anyone's results in my episode, I will credit you. Now, somebody said, have I played with Desmos 3D? And I've played with it mildly. We tried it on one stream, and we're going to try it again later today to see how it interacts with factorials. First, we're going to be on Desmos 2D, and let's just go to the straight up calculator now. And wait. Let's go to the straight up calculator now. And we're going to start on Desmos 2D and graph some factorial things. And we will try what some of them look like on 3D a little later. This website is beautiful. I love them. They're my favorite online graphing calculator, and it looks like they're expanding to have even more tools. Now, shout out to my favorite websites. I'm not a tech guy, but certain websites are very useful. Some of those include the Online Encyclopedia of Integer Sequences, wolframalpha.com, desmos.com right here, Wikipedia, and there are a few others, but those are among my favorites for sure, along with, you know, both due to being what I like to make and like to consume, YouTube. I know there's a lot of problems YouTube has at various times, but despite all those problems, I love YouTube. I'm sort of a diehard fanboy for it. That's why I like making videos mostly on this platform. I kind of quit making TikToks, even though I have 50,000 followers on there, because I just don't use that platform. I love YouTube. So now looking at a few other comments before we jump into our graphs. Thank you to everybody leaving any thoughts. And somebody said it's mostly companies disrespecting the environment. We should vote them out. Yes, I agree. Everyone should vote in the upcoming election. And in any election you can, voting is important for democracy. And I want to leave some political thoughts right here, but I'll just say that this is going to be a very important election if you happen to live in the United States this year, and that I am going to do one stream at some point before the election with my political opinions. So I'm not going to put them into this stream because people don't like when I sprinkle them around. So we're going to do one stream with my political opinions later down the road for anybody who is unsure about whether they're going to vote or who they're going to vote for if they happen to live in America this year. It's going to be a very important one. Now, in general, it is true that companies disrespecting the environment are the big problem. It's not the problem that you are creating your carbon footprint compared to the companies. Of course, we can minimize our own carbon footprint and our own impact on negatively affecting the environment in any way. That does help on a mass scale, but it is much smaller than the amount that would help by passing stricter regulations on giant corporations that are already rich and don't need to cut down any more rainforests, don't need to blow that much coal into the air, and etc. Now, thank you to all the other nice comments, and we're going to just jump in and show, first of all, what it just looks like for them to plot the factorial function extended. Here is when y is greater than or equal to x factorial, where x factorial is extended using the gamma function. Now, how can we alter this further? Well, of course, we could throw another factorial on the mix. I played around with this, and it appears that they don't treat this how mathematically we would write this phrase. This would be a double factorial, which does not mean the factorial of the factorial. It's double factorial, ironically, is smaller than a single factorial. You sort of skip every other number when you're multiplying up to something. So poorly named concept, but also they are, I think, treating this the same as if I had put parentheses around there, where in normal math, note that 2 factorials in a row would need parentheses like this to mean the factorial of the factorial. Now, to begin, just by doing something like putting a trigonometric function we like to play with, like sine, makes it pretty wacky. Tangent makes it even wackier, arguably. Now, what I often like to do is begin with the equation for the circle. And I already have some notes here. I've played around with this concept a little in advance earlier today, and so I do have some equations written down that I'll try. But just for fun, let's build our way there from the circle equation. The circle equation in simplest form, we could say is, I mean, it's arguable what the simplest form of something is, but most would say this is the simplest way to describe a circle. And in this case, we are going to be making a filled-in circle. Oh, I accidentally made a filled-out circle. A filled-in circle. And I can grow it based on A. Its radius is the square root of A. I could put a squared on A, but it's not going to change the general shape of the graph. It'll just change which of these make it which size, but not what a given size looks like. You know, it won't change our possibilities. And so we don't really need to square or factorial variables that aren't our x's and y's, or when we get 3D, our z's, because those, you know, squaring or factorialing those will just be changing what this sends it to the level of, not what the different levels do. Now, somebody asked if 5 double factorial is 5 times 3 times 1, and it actually is. The double factorial is a type of what's known as the falling factorial, and there are many types of factorial. I've thought about for a while doing an episode purely about what are the weird factorial extensions, and that'll probably come at some point. Now, to make this interesting, one of my favorites before we get factorially is if I take this circle equation, putting parentheses right now doesn't change anything. It just separates the terms so that I can now put something like sine on each of them. Well, this just gets brilliantly cool at our different levels of A. Look at these different combos. Now, that looks really cool. So what if we begin here and see what happens when we throw a factorial in? Then we'll move on. I'm just going to plug in some that I've already tested. And what we're going to do is take ones that I found a cool seed of an equation and just substitute variables. Substitute where the factorials are. We're not trying to prove anything today. What we're trying to do is make really cool shapes. So let's throw a factorial after here to start. That makes them more like these columns. Not quite as interesting as it was before. And if we do the same to x, it actually vanishes most of it. Oh, and we get this square-like thing when we get up here. This grid of almost squares is pretty interesting, but we can do better. Let's put the squared in now. I mean the factorial in. Now, it's all blotted out up at that point here. We're getting... Now, usually I find it actually works better to flip this here. So, you know, this is just changing which is red and which is white. The barriers where it's exactly equal and not just filling the greater than part, where it's filling the equal part are these thicker lines. And those ones will remain red, but, you know, if I flip the inequality with the equal thing in, it'll flip where the reds and whites are. So there's that, but we can do better. So I'm going to pull open some that I've found were quite cool. Now, what I'm going to do is start with sine. We're not going to put any squares in yet. And I'm taking away this A because we don't always need the A. Well, no, I'm going to keep the A for this first one. But the A is somewhere else now. We're going to do A times... Well, let's put the A here just to make it look simple. A times x factorial minus A times y factorial in a sign. And let's say it's greater or equal. Now, first let's do A, but that's not what I actually have in mind. Although, whoa, A does look cool. A is still worth it. Okay, I'm glad I tried A on the way to what I was going to show. This gives us a seed of one of the cool patterns that I found. we get these grid-like formations where these eye-like things sort of blink at you. Now here we're not seeing the clearest version of that. We get the seed of the concept, but what really made that start spinning out is to make this side in terms of x's and y's, because we already have an a in the mix. So I'm going to make this side x times y. Now here we get these weird ridges that sort of mutate toward each other, and as they squinch toward each other, the overlapping changes what's true or false. Whoa, there's a big moth thing on the screen. I don't think you can see it, but yeah, you see that moth? Not that big. Luckily not a mosquito like last stream. Now, what we can do to make this more interesting, well, of course we can try with a plus as well. And now what we get is this extra little sort of egg that forms in there. And when the egg hits the wall, it glitches. And I guess we don't get... Oh, yeah, we do get more eggs. Now, what we can do to make this more interesting is, what if we put a factorial on this side? I said it doesn't matter really if we put it on constants, but this side's not a constant anymore. It's x times y. So if I factorial this side, we start getting these weird patterns. So here, look at all these little, like, obelisk things that are, like, sitting in a row. Boom, 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 boom. And here we can see some pretty cool patterns. Some of these, well, oh, I zoomed out. Now, when you zoom to the wrong scale, it just doesn't get the graph very well. When it looks too much fuzziness, that means that they're trying to plot something with a sort of infinite detail that it can't comprehend right there. So zooming in, we could see what it's doing in these spots, but the further I am down this line, the more I'd need to zoom, the further right I am in this case, because they're getting to this optical illusion looking like stairway downward or something. So this stairway continues, is why it's glitching it out. They get really close over there. So these shapes aren't quite really there, but we can see these shapes clearly here. And this is just a at one value. A happens to be 1.4. What happens when we change a? So here is changing a. They're mutating, and we can see what happens in different quadrants. So graphs often have 4 quadrants. You know, 2 variables are going to cause that sometimes. And so, ooh, here's at 0. We just get this. There are no points where it's equal, but the inequality holds at different points. That's interesting. And looking at the quadrants, like there's one where y is negative and x is positive. There's one where they're both positive. There's one where they're both negative. And there's one where x is positive and y is negative. Or I might have said those backwards, but you know what I mean. And looking at those, we can see interesting things sometimes. Here, we're going to have some symmetry down a certain axis. Like here, the symmetry appears to be somewhat, although it's a weird type of symmetry, I guess, with these flipping in a way, related to the y equals x line, reflected around that somehow. But we could see, as we go forward, these little egg-like things sort of collide into bigger ones and then vanish. And down in this quadrant, we're getting these more like spiky guys. So, where do we go from here? Well, first, we just have to try overloading the system in a way by throwing an extra factorial on either side. And when we throw an extra factorial on the left, we get a pretty cool thing going on here. So look at what happens when I change a now. And I'm going to zoom in on this thing. So when I change a, these things move, well, right now they're moving outward. So let's say a is down here. Now they're going to be moving inward. These different things are moving inward, but where they overlap, oh no, now they're moving outward, I guess. Other direction would be inward. And wherever they overlap, so inward actually, like, it's easier to observe this, because outward, it's like, where did they come from? Inward, we can, wait, this is weird. Why do they, is this like a weird optical illusioning me out. It looks like they're going outward when they're going inward. Different parts are doing different things, but we can see these things colliding and merging. And what's going on down here in this graph? Well, a lot of stuff. We start getting these strange squares when we do this. we start getting like this square of the grid does something different than this square of the grid. And like, look at right here. This eye is going to sort of do its own mutations. Now look like at this one right now. This one does its own sort of mutations. On these realms, they sort of stretch more together, whereas down here, they're almost more contained in their own squares, but we also pretty quickly get to a point where I don't see any. So let's fiddle with the equation a little more. In between, I should probably set a to 1. Let's try and remember to do that in between changing equations. Now, where we can go from here, what we can try is taking other trigonometric functions real quick. So real quick, let's try a similar thing if I did tangent, which gives us our own weird eyes blinking inward and outward. Or what happens, and you know, let's get ready to have a new one. I'm going to copy this into a new color because it often looks extra cool when we try like two variations. Like, what if one's plus and one's minus? Now we can see them mutate together. And some things they do are independent of each other, and other things they do are, you know, rely on the same asymptotes or such. We'll mute that one for a minute, visually, and let's try, first secant does some cool stuff often, and then let's try real quick the hyperbolic ones. Not sin. Yeah. Now here's where we start to get to some really strange ones. So, you know how I said things rely on squares here in a strange way? Well, look at this. We can see this square cut out of this circle. We can also see down here, like this square filled in apart from a blob inside it. So changing A, we can note what I meant about some parts of this are independent of each other and just like are how they want to be, or are within their own range. Other parts of it will stretch onto each other and affect each other. So, real quick, looking at our comments, somebody said, when are they going to include the W dimension? If you mean a 4D graph, I suppose we could consider a 4D graph to be like if I had a 3D graph that was actually 3D in front of me, and I was observing it change in real time, and I analyzed it changing in real time as I slid in A. Like, if I play A changing right here, we sort of have a 3D graph, because we're seeing slices of it at different A's. A is sort of like a third variable if we're seeing each of these as a slice of it. So if we had a 3D graph with a one constant like variable that was evolving, which could be like me watching this over time change, theoretically we could treat that 4D-ish in a way. Now, I will leave more thoughts in the future at points about my opinions about the fourth dimension. I think it's very important, and the only spoilers I'll give you for now is that I think the fourth dimension relates very closely to fractals in a way that no other people have analyzed yet, that I want to explain someday. And I think that, in general, the fourth dimension makes more sense than some people think. And we are living in it in a weird way. On the 4D bookshelf of time, in a way, we are a certain book on there. Now, in general, somebody mentioned one that's a bunch of circles. So let's try it real quick. That sounds kind of cool. So we can always edit it if we find anything interesting. So I'm taking this equation from Voider here and seeing how this one looks. Oop. Yeah. What's wrong with that? Why don't they like that? Cannot use an inequality here. They don't like it in this form. Yeah, the inequality doesn't make sense there. Oh, that's a separate term you have there. It's not a term, it's like a key to it that y must be greater or equal to 0. I guess we'll just look at the sector of it where y is greater or equal to 0, if that's what you mean. And this does make a bunch of separate circles, like these little eggs floating on the... Oh, no, yeah, y above 0 would be here. Yeah, so these little eggs, those are pretty cool. We could probably mutate these in an interesting way. Can we make these eggs turn into anything? Well, like, what about y plus a? You know, no, they're just sliding up and down sort of with that. What about if I stick one on there? Oop, now the eggs are mutating. Oop, what if I stick a factorial right there? Oh, now the eggs turn to different shapes. Look at that egg. Don't want your chicken to lay that. Now, these are cool. Thanks, Voider. And getting back to these, this one is quite cool. And we can make it even crazier. We're only about a third of the way through the notes I have here of fun ones to test. Now, I'm going to leave these available. Actually, I'm just going to leave this one available for later, because this one is pretty cool, and it establishes a pattern we're going to see. We're going to see that this quadrant and this quadrant are going to have curve-like getting closer and closer things. This quadrant is usually going to have some egg-like things that affect each other. And this quadrant is going to have these square-like things that sort of mutate like little eyes. So now let's go to another example. We haven't incorporated division yet. So let's try sine of x factorial divided by y factorial. And let's say that's going to be, first we're going to say it's just greater or equal to, okay, I think there are mosquitoes here like last time. I know that distracts me mid-thought, but I just felt an itchy bump on my leg, and I just saw a mosquito-looking thing out of the corner. Last time you saw, I killed that mosquito dead, and it was one of the biggest, maybe the biggest one I've ever seen. So I hope this isn't its cousin. Now, here we have... That's pretty cool, but what looked cooler in my notes, and black sort of obliterates the other colors when we're putting them on top of each other, so we're going to make this one green. Now, when I added some factorials here, it got extra cool. So here, I've added a factorial on each side, and look at this. This is like the weirdest graph ever. Imagine you first analyzed the positive quadrant. Okay, you're like, okay, there's nothing in this quadrant except this little egg that slightly overlaps there. Then you're like, okay, what if we look at this quadrant? Okay, I have stripes, and then I get this weird egg-like thing, and then everything gets so close it forms these weird curved patterns in multiple different directions. And now I'm like, okay, what if I look at this lower quadrant? Well, now everything's these dense things, but they also have cutoffs where the integers change. Now, this is causing a lot of glitchiness on the computer. It's not handling that very well or clear, but we can see hints of it here with what they are able to view. And here, look at this. These ones evolve until they sort of hit this strange state that's almost grid-like. Here it looks exactly like a grid. It's like a check. This is a crazy version of chess. Imagine if this is your chessboard. Okay. Now, to evolve this a little more, one more one that could be fun to try could be what happens if the x and the y are in parentheses. Oh no, are in parentheses right there before the factorial. That sort of obliterates these dimensions. I don't like that as much. But what we can try also is throwing an a in the mix just to evolve things. Now I can do strange things with my chess setup. If you're able to do this as a move, it's an even crazier version of chess. Now, let's move onward to another type. Here's one that I found was, and we'll keep these as usual. Like, what does it look like when I have both of these together? You see how sometimes they align to similar patterns and other times they just do their own thing? But that's cool. Red filled in some of the squares of the chessboard, but not all of them. Okay, that's weird. Why didn't red fill it? Red tried to fill them in, but it got obliterated. But it filled in these ones properly. These graphs are, they always blow my mind. Now, moving forward, let's see what happens with one of my other notes, where I take the sign of x plus y. Oh, we'll put that out of the parentheses. X plus y with a factorial, and we're going to just make it greater or equal to something really similar. We're even going to copy paste this and just turn the plus to a minus. And this one is simple, but simple can be pretty cool. This one actually repeats a pattern forever instead of glitching out at some point. Look at this pattern. This would be a cool board game setup where you have these little, alternate colored circle things. I'm not sure how the board game would work, but someone designed it. Somebody asked, can I explain how these things happen? Well, I'm going to make an episode sometime that explains some of the simpler ones, like near the beginning of this when I showed just sign on the circle equation. I'll try and explain some simpler ones like that. When I make an episode about the gamma function, that will explain some simple factorial ones. But this is actually one of the cases where computers can help us in ways that humans kind of can't comprehend, where it would take a whole paper sort of to describe exactly what any of these given equations is doing. And so instead of writing a paper on a given one, we're sort of combing through a lot of different possibilities. Now, with that said, the factorials are interpreting something as a gamma function, which I'll explain someday. And the sines and other trigonometric functions are using trigonometry, essentially, to create more complicated versions of, like, if I had y equals... Like, basically, y equals sine of x would look like that. Y equals hyperbolic sine of x would look like that. Y equals tangent of x looks like that. And y of x factorial extended with the gamma function looks like that. And we're sort of just doing crazy combos of them. And this type of stream is less about explaining why a mathematical thing works. I like doing that as well. But this type of stream is more about showing the possibilities of almost making art using mathematical graphs. Now, moving forward, something similar to this we could try is, what if we throw more factorials on the inside, because this one's sort of simple, to complexify it a bit. And one idea I had is, well, what if we put it on the x of one of these and the y of the other? So, because then we get a weird sort of symmetry in portions, maybe, and we do. But other portions are less symmetric. Now, like, for example, right here, we don't see symmetry on a clear axis with these mutant glitches right here. And this is like a mutant version of that pattern we saw before. This is that pattern we saw before stretched in a weird way. And that pattern we saw before is actually here too. The pattern we saw before is right down here. Where'd it go? Where'd you go? What the heck? I swear the pattern was... Okay, it's further down. It's down here. Look at this pattern. It's back. But now it's only on one of the quadrants. And in fact, it cuts off a bit before the quadrant. It gets glitched in this last... rectangular bit of the quadrant. And yeah, I like how somebody mentioned the grandma's kitchen tile, and I was thinking about that since you commented, and now you're like, oh no, my grandma's kitchen tile. And yes, this is what happens when you spill a very strange potion on your grandma's kitchen table. So, somebody asked, can I make a face or a tree from the graph? Now, we could make, with a bunch of different equations, a really proper looking one. You can even do it with a single equation using this thing that the mathematician Fourier invented, where you sort of have a bunch of circles on each other. So in a way you could consider it different equations together. We could combine a bunch of different terms that specifically made a face. Maybe someday we'll do that. However, I like to look for faces in trees that emerge in the graphs that we didn't intend to be there, where I see it as almost a sort of evolution, and maybe it even has its own form of natural selection of how the math comes to similar shapes that we see in our world. Some of that can also be explained by this concept called pareidolia, if I'm pronouncing that right, where humans see face-like things in things where they're not there. And that's an evolutionary response to have humans be good at responding to their environment, such as threats. But we're stuck with some genetic things from our evolution. So when you see like some butterflies, you're like, it looks like eyes on it. Sometimes they did that for evolutionary reasons. Other times you might see something, you're like, that looks like a face. And it's like, well, that's just you being a human trying to see faces and things genetically. So we see a lot of things in these streams. In past streams, I've seen things that look like eyes, flowers, different types of insects, faces, doorways, staircases, all sorts of things we've seen resembled in here. And I like to ponder the way that mathematics coming to this conclusion of sorts could relate to the fact that these are shapes that we have seen nature evolve. And so perhaps there's some strange natural selection at play within here as well. Somebody said they came here to buy clocks. Now, I have to reset up a lot of clocks. A lot of my clocks are in different zones right now and not clearly on the wall and stuff. So even if I brighten the background, we're not going to see a ton of clocks. Grandfather clock still right back there. But there will be more clocks gotten soon. I'm going to visit some yard sales and such to get some new grade -3 clocks. Because as a reminder for anyone who missed the very beginning of the stream, and let's stick a freaking A in here to play around with while we talk. And for anyone who missed earlier in the stream, that's changing it at just a normalish scale, at least for the kitchen tile pattern. So we're going to be weird, and we're going to put the factorials both on one side, and we're going to put the A's on the other side. Now, for anyone who missed earlier in the stream, I will note that, like I said, there's only 2 main episodes on my combo class channel remaining in grade -2. The next one will be sort of a mathematical finale related to things I've proven about prime factorizations. Then there will be a finale where I'm preparing for grade -3 and doing a documentary of sorts about grade -2. And that will include camping in the combo classroom. It will include flashbacks of all the craziest injuries, animals, plants, and etc. that I've seen this grade. Some of which you've seen, some of which you haven't. And then we'll move on to grade -3, baby. Now, this one's sort of interesting, but the less kitchen tiley for sure. Now, somebody asked, how would you learn mathematics if somebody told you to do it from... Let's put a few on just to see what happens. If somebody told you from scratch. It depends what you mean from scratch. Like, you know, as Douglas Adams said, to bake an apple pie from scratch, you need to first create the universe. So from scratch is a, subjective term. Because am I assuming that the person learning math from scratch already did high school level of math, or am I assuming they at least did elementary school level of math, or what? You're going to want to take some classes, but theoretically, if you had classes even up to a relatively simple level, you could go on your own, even if you had no classes, let's say. My recommendations are, in addition, do personal investigations, which will be a topic explored in my next episode. Reading a lot of stuff. Read to learn about math and take notes about what you read, and take notes about what connections you find between different concepts. Now, going forward, let's try a few more cool ones that I thought of. In a minute, I might have to run inside and grab some water. Sometimes I need to take like a 3-minute intermission. But if that is the case, I will be back quite soon. Because I'm having fun with this. And we're only halfway through some of the cool ones I wrote down as ideas. Not to mention, the last thing I wrote as an idea was something that another comment also mentioned here, which is try these on 3D. Now, first let's try one more, then we're going to do like a 2-minute intermission where I'll animate some stuff, and then we'll do some more streaming. And also for my diehard combo fans, Do not leave. Instead, leave a random question in the chat. So, here's one where we got sort of the circle equation mutating. We haven't tried exactly this one yet. Here I have the circle equation with its sort of sign mutation. Oh, no, you can't see that anymore. We're under the level you can see it. I'll put it higher there. So here we have sort of the mutated circle equation that we did before. When I just put this over A, this was this. But note that it passes this state right there. You see this shape? Now when I go xy factorial there instead, not at this level, oh, come on, go away. Okay. Not at this level, that shape went away, but at a different level, I meet it. I wonder if that different level is related to the factorial function having to offset things by 1 to match the common gamma function. Now here, we've created the shape we had before at a certain level of this with a certain level of that. 0 for A sometimes obliterates certain things going on, because we got 0 factorial over there. Oh, that's why. 0 factorial is considered 1 because, for 1, it's the empty product. For another reason, factorials can be also interpreted as the amount of ways of arranging that many items. And technically in math, you say there is one way to arrange 0 items, which is, you know, the not having any way. And so x factorial is 1, and so 0 obliterated that, turned it to 0 factorial. And so this is saying that this circular thing was greater than or equal to 1. But here's the cool thing. Sometimes when we mutate the formula, if we inch it even a tiny bit off, it completely changes and it doesn't resemble the cool formula I like with the signs and stuff that's super simple. Here, though, I can inch it a bit and mutate it. Now we're seeing like alternate universe versions of this one shape. And when we change certain things about equations that at a certain state are the same as another, we get to see all these cool cousins of them of sorts. Ooh, and look, it's like painting a weird checkerboard up the side. Now it's painting it over there. Okay, I'm going to run inside just for a really quick intermission. I'll try and be less than 3 minutes. If any combo lords leave early, make sure you've seen my new episode in the description about cicada math, and make sure that you're ready for some really cool end of grade -2 stuff. Hopefully you'll all stick around, and feel free to leave a question in the comments or chat or whatever if you want me to answer that in a minute. I'll be back soon, and for now what we'll look at is the animation. That's always fun to have in the background. So we're going to animate it as slow as we can make it. And that, you know, may prevent glitching. These look cool at different areas, so I don't know if this is the right zoomed scale. But let's just go for having a few of them on the screen. Oh, that one obliterated a lot. Let's go for just these ones on the screen right now. Now, this is going to evolve slowly. So I want you... Okay, we're going to put this one on too. Hopefully it will not eradicate. Oh, and before I take my quick intermission, thank you to whoever left a donation. Those are very helpful and useful. I actually just invested in a new camera, and that's the type of thing I spend my money on. Like, I was going to make a bonus video today, but I actually went and got a new camera so I can make a better bonus video tomorrow. So donations like that help a lot with our combo operation. Somebody who left this, called Dale Garner, noted an equation that they really like. They said it's nothing to do with this, but it's their favorite. So we'll try and look at that one later in today's stream. I'll be back shortly. Alright folks, I'm back. It's very dark back here. Gotta be careful not to trip on stuff. Like I said, I'm gonna go camping back in this classroom soon. And so I've already set up a corner where the fire pit's gonna go. And the fire pit needs bricks around it for safety. I know many of you do not think of me as an example of fire safety, but believe it or not, I am. As we'll see in the upcoming finale, I have only burnt myself on random little candles I wasn't paying attention to, not on any of the fire stuff you may consider a stunt. So, this is cool. I like how we can see them mutating, like I've noted, sometimes in each other's same squares, sometimes on their own sorts of arrays, and quite beautiful. Now let's move onward to some other stuff, and since, Dale Garner left not only an equation but a donation, let's test his out real quick. I don't know how Desmos is going to interpret this. Can I just paste that in? It's not in the form I've usually put into Desmos. It's also not letting me copy paste it. Let me just try and type it in and see if somehow... okay. I can't copy paste it for some reason. It's not letting me copy paste it from the chat to Desmos. I'm going to have to test your equation later, Dale. But I will do that, and I'll try and show it in the next graph stream. Speaking of which, while I have a bunch of people here, leave comments if you have preferences of the streams are sort of bonus content of what type of streams you enjoy. Do you like when we look at graphs? Do you like when we look at bad proofs? Do you like when we look at stories from my life? Do you like when we do a natural or cooking related or food related activity? Do you like when we... what else are examples? Make music in the streams. I've made beats before. Before long, you guys, if you convince me, I'll do a stream where I will show you more of the music I've made. What type of streams would you like to see? Now, looking at a few more 2D ones before we go to 3D, we are going to try a really simple one. Here was an example I was almost going to show at the beginning before I got sidetracked, because it's quite simple, but still looks really cool. I like graphs that we can explain in, like, how few of symbols can we take? And let's treat, like, sine as one symbol, because it's sort of an operation, x factorial as two symbols, and so on. What's the fewest amount of symbols that makes an elaborate picture? That's sort of a subjective but interesting question that sometimes is on my mind. How can I complexify them to get a crazy state, but then maybe simplify them to get to an equation that's more digestible while still having enough of that complexity? Some of them have more than enough complexity, and even if we had half their complexity, we would look pretty beautiful. Now, as an example, let's just try x factorial divided by y factorial is greater than or equal to x times y. That is a very simple equation. And look what we get. We get now more than 4 quadrants. We sort of get 8 quadrants, although these ones do the same thing in 2 of their quadrants. These ones do different things in 2 of their halves. Well, now it's not quadrants. I guess, do we call them octants? Actually, what do you call an eighth of a graph? An octant? So, we get in our different octants. This one's checkerboard. This one's lines. This one's half filled, half not. I mean, relatively half filled. It approaches that ratio. Oh, no, it's not half. It's not on x equals y. But it's going to approach the ratio of the slope of this, if this is a straight line, or approaching a straight line. This one approaches having all of it filled, as far as we can tell. And this one approaches, I guess, having a quarter of it filled, because half of it is checkerboard. This one, we can tell, approaches having half of it filled. So that's sort of, well, no, it's not a quarter of it filled. It's half of whatever we would calculate from that slope, because the slope, it's not cutting it into octants. It's a slightly different angle. Now, of course, we're going to see what happens when we throw an A one place or two, just because we can mutate it a bit. This one stretches them a bit, and then they flip and vanish. A over here instead. You got to be careful. If you put an A on the top and the bottom, does nothing with more symbols. They'll vanish. A over A multiplies it by 1. So careful not to use symbols that are unnecessary if we're going for our goal of simplicity yet complexity. Oh, here we get a different ratio filled in because now it's sort of flipped, but we still get our checkerboard. That checkerboard does not want to die. Now, somebody is mentioning a polar coordinate. We can always test those. We're not going to do a ton of them today, but let's see what the polar coordinate somebody mentioned was the radius. Polar coordinates we've done in a previous stream. Not going to explain them here, but they relate to circular curves. Now, I think I just typed theta. Yeah, typing theta gets me it. So yeah, this was the one that generated previously a lot of what I said looked like flowers and insects. And of course, inequalities I find look even cooler, but we'd flip it in this case because then we can see sort of a little more of what's filled in. We have looked at this before, and it's really beautiful. Thanks for recommending it, but you know, all we'll do today is stick a factorial in there, not an at symbol. Stick a factorial in there, and it doesn't like it. Oh my god, it's okay. Sticking a factorial in there really glitched out the computer. It's having like a hard time switching n values here. Does it always blot it out? Yeah, factorial's not good there. I'm worried this will even slow down the stream, whatever that did. Anyway, we'll do radial coordinates mixed with factorials another day. We already got some other stuff to try. Now, one more, that this one I noted can make some islands. Now, the reason I bring up factorials in this stream is partially because in the last, not the last stream, but the last stream that I did graphs in, somebody mentioned, I forget their name, but if they watch this, you know who you are, that I should throw a factorial into a certain graph that I had been making, and it made my whole graph condensed into a circle. While it's cool to have each quadrant rippling out to infinity, it can be even cooler in a way to have this little condensed zone that it's all within. I won't say cooler, but I'll say cool in its own way. And I found, again, you know, an example of one that's a little simpler than where we did it last time, that will create a little island. And then we can fiddle with this to put different stuff in the island. So we're doing cosine of hyperbolic sine of something reminiscent of the circle equation, x squared plus y squared. And we're just going to, for now, make that greater than or equal. Okay, I'm going to make it a, but just for fun, let's make it... Oh, I forgot. These need to be higher for you to see. Now, let's say this is going to be greater than or equal to xy, just for a second, just see what that looks like, but mostly we're going for a. Somebody said they didn't get the chance to tune into a beatmaking stream live. Those are the only music-related streams I've done yet, are me making beats. However, we could get streams someday that are me playing live instruments, or me rapping or singing over my beats, or things like that. Now, I've written many songs, and believe it or not, creating musical albums is almost or maybe as big of a goal as creating my videos. I've just, you know, postponed it while I've been working on this, and there will be a lot of Demotro albums out someday, and I have released a lot of albums under previous names as well. A lot of those were just distributed on CDs around my high school or whatever, or on Dat Piff before they got taken down, or stuff like that. But there will be Demotro music as well. Now, if people like that, leave a request for a musical live stream, and what your favorite type would be. Me making a beat, me rapping and singing, or me playing live instruments. There will be music theory lessons as well. I used to work at a music shop just a couple of years ago. I was a music teacher, and as my day job of sorts. And there will be music lessons in grade -3. At the very least, at some point in grade -3, I'm going to do my guide to chords. Musical chords are an important concept within it. And probably the same grade, if not the next grade, I'll do my guide to scales, and we'll go from there. So, here, where's my island? I swear I had an island. Oh, what I did is I forgot the factorial. That's a crucial part of today's thing. There we go. Now it's like, okay, I got this island. That's kind of boring. It's just grayed in. Well, what if we evolve it? Now my island's looking a little different. Now my island looks all blurred on the outside because it has closer and closer concentric circles contained within this thing. So, how can we evolve this circle? Now, one example would be, what if we put an X and a Y on the side with the A? Well, now it ate some of the circle. Okay, there it's back. This is like you're eating an apple from both sides. And, oh, they left the core. Yeah. Oh, my God. This is actually like eating an apple. It's like okay, going from 0. It ate the apple and left the core. So, for whoever was asking for trees. Oh, whoa. I wonder if that comment was before or after I said that. A comment just noted an apple. And we have like a few minute delay, I think. I think that you see me a few minutes after this is happening. I don't know. Anyway, it is an apple. For whoever asked earlier if we can design things like trees, well, we designed something that fell off a tree. And, if the apple doesn't fall far from the tree, then the tree must be near. Although that expression, as I've noted, is terrible because an apple's sole purpose, evolutionarily, is to spread the seeds as far from the tree as possible. It's like, what? What do you mean the apple doesn't fall far from the tree? If you count, the branches spreading as far as they can, and then hopefully the apple being evolutionarily carried somewhere because it got really yummy for animals to eat it and carry it somewhere or poop it out somewhere. The apple's designed to fall far from the tree. Okay, sorry, I take offense with some random idioms. Not actual offense, joking offense. Now, that one's fun because we got our island, so how else can we play around with our island? Of course, what we could try is switching these for different functions. When I made it a hyperbolic tangent, though, it got not only not islandy, but boring. What about a hyperbolic cosine? Pretty similar to sine. And what about a hyperbolic secant? It's boring. Why? For some reason, some get boring. Sometimes maybe these two trig things, if I analyzed them, cancel each other out in a way. Because some can be described in terms of each other. So, you know how I said don't put like an A over A accidentally in your thing, because then it's just terms we don't need to make the beauty. Sometimes these will cancel each other out in ways you have to analyze to note, because one of them could be 1 divided by that one, and then you have this and that combined. Anyway, what if I do different combos? No, for some reason, when we try and get this outside one acting crazier, it's not as nice as our good old hyperbolic sine. Now, we are just going to throw a few more factorials in the middle, and this is an apple that's sort of a dud. Oh, this is a sideways version of somebody. Here, we'll put it on Y instead to get this again. This is a simple. Oh, that's cool. I like this. Okay, first we'll have it on both. Okay, I like that. Yeah, that's pretty cool. Now, putting it just on Y, this is the one that somebody noted, is kind of similar to, if I get it the right dimension, a YouTube play button. It looked even more like it the other day. I don't have the play button I own. I have one for this channel. I don't have that in the classroom because it would get destroyed too quick. And let's get a play button for the other channel. Everyone make sure you're also subscribed to my main combo class channel. Now, throwing it on both again because that looked cool. Let's see what happens when we try even getting crazier. Remember when we had it on this side? We're going to put in factorials till we break it. So we broke it. No, we didn't. We fixed it. And now we are inside this squircle. A square circle. But inside this squircle, we get different things happening. When I go negative or positive, it's sort of a symmetrical version, it seems, of each other. Where it flips it a bit. Those are pretty neat. Let's zoom in a little to see a better sense of what's happening at these closer scales. Since it looks kind of symmetrical, I'm just going to zoom in on this quadrant. Now that's pretty cool. So there you got a particular island, and there's an equation that we had a while ago that I'm going to re-look up sometime to play with variations of in our next graph stream that made so many islands. So keep an eye out if anyone plays with this on your own and want to mention an equation in a future stream. Keep an eye out for ones that create a bunch of different islands. Those are pretty cool. Now, removing that, we get a larger squircle. I just took one of the factorials out because it's complicated enough. And we can do that in various ways. That is most of what I have for this. Let's try here also. I noted if I add an x factorial here, it gets trippy. And that was even when I just had it less than a. So, okay, well now it's trippy in a weird way. We only are affecting, oh, whoa, I thought we were only affecting that slice. Okay, we're only affecting this slice when we're in this range, the gap. But now we go here. This is such a random looking gap. And now we're only affecting that part. So the one that looked even, oh, what did I do? Okay, that's right. And then the better is if I add a y factorial 2. Now look at where the two gaps cross over and we get this little square and this thing. Now when I mutate them, okay, it's eating away at the outside. If I go the other way, it's filling in the inside. Ooh, and it starts creeping up on those ones too. All right, now that's pretty cool. Here's what we're going to try now. For the end of our stream, we're not done yet, but we might be wrapping up before too long. We're going to try if 3D can handle any of these. Now, 3D, as they note, is beta here. They're still sort of testing how this works, and we are trapped inside a square. The reason for that, I've realized, is that if they make it go on forever, graphs look too clogged up. I'm assuming that's the reason. It looks just like blotted and filled in if we can't see a certain range of it like this. Now, what happens if I just look at something like z equals x factorial without y being in there? We get these guys because y is sort of staying the same, but we get these slices. Now I can zoom, so we're looking at, when I zoom, it looks weird like I'm shrinking it in the square, but really what it's happening is I'm looking at a bigger square. Now, what if I also add a y factorial there? Now this is z equals x factorial times y factorial. I love it. Now, these ones that look like they're spiking upward and vanishing probably are still having a really thin spike going up. It just got too thin to show. That's my guess. But, oh, I love it. Look at this little cup right there. Now, if I zoom out, does the cup keep a lid? Does it stay like a funnel? Yeah. Or does it get closed? Oh, no, I got lost. How do I get back? Oh, no. I don't know what to do. If I zoom out, I'm not at the center anymore. How do I move it? Oh, come on. What? How do I get... Okay, I'm restarting the page. Okay, we're back, and now we're going to put in some of the ones we had from before. So let's see if it can handle this, and we're going to change some of the stuff to a z. So now I switched one of the xy's for a z. Okay, we feel... Oh, yeah, at the right range, it looks really cool. Look at that. Oh, my God, look at this whole world. Okay, now when I evolve it, it starts growing. Oh, look at these little like staircase bridges. This is so, I love this. Okay. Oh, we passed something notable. Where was that notable phase we passed? There. Now all of a sudden it looks like a, at the phase like one before this, this one looked like an office. Wait, what? Oh, 0. Yeah, 0 is going to make stuff boring sometimes. But doesn't that look like an office floor plan or something? Like where a bunch of telemarketers work or something? And We can spin it. Yeah, we can. But this shows that factorials can do wacky stuff, and that if we're at the right level, we are going to see really cool stuff, and if we're at the wrong level, it's just going to look blotted in too much. So let's try the next one. Okay, so this is flat. That's because I haven't put z in yet. We have to figure out what we're substituting for z. We're, in this case, going to take another xy over there and just turn it to a z. Whoops. Oh, I like it. Okay, we have a 3D version of the thing. Oh, I like it. Okay, I have to see what a 3D version of, like, my favorite equation looks like. Remember this one where I just said this is greater than or equal to a? Wait, what is extend to 3D going to be? I was going to add a z somewhere. But look, we're seeing a flat version from an angle of the thing I showed before. And what is this going to do? Oh, it just made it tall. Okay, no, don't. I want to add a z term that matches. Okay, so this, in a weird way, is the 3D version of that thing I showed before, of one of my favorite equations. Look at all these slices. Remember I said that we made a hamburger factory in a previous stream because it genuinely looked like that? Here are all the hamburger patties waiting in the shelf, and this is something. Look at these. This is like the 3D version of one of my favorite equations, which is just a glitch on the circle equation. By a glitch on the circle equation, I mean if I take out the signs right here, it's straight up going to be a sphere. What went wrong? Something went wrong because I tried to match the circle equation too much and we're in 3D. So never mind. In any case, it looks cool with the signs in there. Next equation. Now, let's try this one. As usual, we start as just a different angled version of what we already saw, because we don't have a z term in there. Let's add a z this time instead of replacing anything. So we start with this. Got a little egg in the corner of your room. And the egg mutates a little bit. That a isn't changing that much in this case. Let's stick the a somewhere else. Whoa. I don't like that cube right there. Let's try the next one. We got plenty to try. What does this one look like 3D? Well, you know. Oh, this one is the one that had a fixed little squircle it stayed within. I wonder if 3D will get a... What do you call a 3D squircle? So a squircle is named that because it's a square-like circle. Or a circle-like square, depending how you look at it. How would we define the cube, or how would we name the cube-like sphere? The cubier or the sphube? I kind of like sphube, even though it sounds weird. So sphube will be our term for the 3D circle. Or maybe spherube, because sphere... No, sphere... Okay, no, sphube. It's not a great name. We're going to need a marketing expert in here. Okay, so adding a z somewhere to make this 3D. Nope, if we put the z there, we might also need to match the z in here to make it have the similar trait. Yep, when I match the z in both places, we are now in a sphube. And now I can, we're going to zoom in a little bit because it's contained there. And we're going to evolve it. Now this evolution isn't, oh, I was going to say it isn't changing much, but sometimes you hit a point where it does change it a lot. That's pretty neat. All right, let's try one or two others. These are some others that we had in our mix. What does this fellow look like 3D? Well, this was our grandmother's tile. So you remember the grandmother's tile? Now, what's going to happen when I add z in a similar fashion? Now here, Whoa, that was right there. We got, wait, is this grandmother's weird sculpture or something? Now, here, it's sort of ambiguous how I should put the Z in to match it. Like, do I do plus or do I do minus? Let's try each. If I do plus, it looks like this. We can still see that pattern in a way, but then they skew off at these weird tunnels. And if I do minus, it looks very similar. No, it doesn't. Yes, it does. Now, what if we try just screwing with this a little bit and multiplying the 3 terms together instead? That looks the same for some reason, unless it didn't load it. Okay. What the heck? Okay, no, it's going really slow. It's having trouble loading this. Okay, no, actually, yes, it is different. It did just take a while to load. This is why it took a while to load. It was trying to describe all of this stuff. We're not centered again. To do our last graph, I'm just going to restart this because it recenters us. How do I recenter it, folks? Now, here's one more that we had in our roster that we might as well try 3D. That looks pretty cool, and we can mutate it with A. Ooh, that's beautiful. Now, what happens when we put a Z in? This one is obvious if I want to copy the pattern. This one, again, I can choose if I add or subtract. If I add, here's what we get. What went wrong? I need something. Oh, no, it just took a second. Yeah, these just go really slower than I'm used to because it's trying to calculate something pretty crazy. Now, is there a value where this is more visible? I switched A, and I have to, like, wait because I feel like it just took a while to load it. If I put A up there, okay, now it's loading quicker maybe? No, this A is going to take a second. It's going to change. Watch. There. Now, this is pretty crazy and complicated, so to wrap up, let's just try a few simpler ones. Let's just see what happens, like if I sine multiply them, and I say it's more or less than them factorial. That's pretty cool. We got these different, this is a different sort of octant that we were joking about earlier. Different octants of our 3D graph. Now, thank you to everyone who's been watching and enjoying this. I think I am going to wrap up soon because it's been like an hour and 15 minutes. And also because it's like almost 10:30 p.m. here. And I don't want to be loud super late out here for the neighbor's sake. So we're going to wrap this up relatively shortly. If anyone has any last thoughts, feel free to leave them now or later in the comments on the video, which always help. As a final reminder, make sure that if you quit the stream now, or you'll have to soon when I quit it, that you've seen my episode about cicadas I put out a couple days ago on my combo class channel. That's linked in the description. And make sure you're ready for 2 more really cool episodes on that channel before grade -2 is done. One mathematical sort of finale and one documentary-ish sort of finale. And thank you all. I love you all so much, and I do have a lot of cool bonus content planned, like I mentioned. I got a new camera today, not the one that we're filming on now. This is just on my computer. But, that state looked cool. But a camera to film my regular videos on. And so, that might look and sound a little better, and I'm going to test it out tomorrow. So, thank you all for joining me. Big, cool plans, and I'm very excited about next episode containing some proofs that I invented myself that may have never been done before. Anyway, there will also be some bonus videos on this channel. Somebody said you could 3D print these, and that would look pretty. Remember that the cube is just showing a slice, so I can zoom out and see it's taking a second to load. It looks like that more zoomed out. So you'd have to pick a slice to go with. Oh, that looks pretty cool. However, similarly, you'd have to pick a slice of the 2D ones to be wallpaper. So I do think there should be more houses painted with wallpaper, or even shirt designs or whatever, of some of these graphs, or these cubes should be 3D printed. And if anyone wants to turn any of these into art, I feel like they are not copywritten in any way because they are math equations. You may have to either credit Desmos or design the graph yourself somehow. But if you want to 3D print things, wallpaper things, or whatever, you should. And if you happened to get your inspiration from me for it, all I want is a little credit, and I want you to make cool stuff. So, thank you all. Love you all with all my heart. I'll be back again for more cool stuff soon. And until then, hope you all have a nice day or night. And if you're bored, remember to fiddle around in similar ways. I love doing stuff like this. Feels awesome. And you might see some cool, weird eyes and trees and fire and flowers and all.